Hey everyone, in this video, I will be presenting my project on the computer torque control of a 4 degree of freedom robotic manipulator using MATLAB Simulink and Simscape multibody. I will walk you through the complete workflow starting from mechanical design, moving into simulation and dynamic modeling, and finally showing how nonlinear control improves the robot's performance. Now, you must be wondering why robot control is challenging. At first glance, controlling a robot might look simple. You give a command and the robot moves. But in reality, robotic manipulators are highly nonlinear systems. The motion of one joint affects the others. Gravity continuously acts on the link and inertial effects changes as the robot moves. Because of these factors, achieving smooth and accurate motion control is a challenging task, especially when using simple control techniques. The goal of this project is to address these challenges using a model-based control approach. I designed a 4 degree of freedom robotic manipulator, developed a physics-based simulation model, derived its dynamic equation, and implemented computed torque control. The performance of this controller is then compared with conventional PIT control to clearly demonstrate the improvement. Here, the development begins with the mechanical design of the manipulator in SolidWorks. The robot consists of 4 revolute joints arranged in a serial configuration similar to many industrial manipulators. While designing the model, the focus was not only on geometry but also on creating a structure that could later be used for dynamic analysis and control. Once the design was finalized, the CAD assembly was prepared for simulation. Then the SolidWorks model is exported into MATLAB using the Simscape multibody link. This step is very important because it automatically transfers physical information such as link masses, center of mass, inertia tensors, and joint definitions. As a result, the Simscape multi-model directly reflects the real mechanical design rather than being an idealized or simplified representation. As you can see the robot model here, to control the robot accurately, it is necessary to understand its dynamic. The motion of the manipulator can be described using the standard dynamic equation, which includes the mass matrix, Coriolis and centrifugal effects, and gravity torque. Here, in this project, these terms are explicitly computed using the physical parameters obtained from the Simscape model. This dynamic model forms the foundation for the control strategy. The complete system is implemented in Simulink using a modular architecture. A reference trajectory is first generated, which is then passed to the computed torque controller. The controller computes the required joint torques which are applied to the Simscape manipulator model. Joint positions and velocities are fed back to close the control loop. Now, computed torque control. It is a model-based nonlinear control strategy. It uses the robot's dynamic model to cancel nonlinear effects such as gravity and joint coupling. Once these effects are compensated, the system behaves like a set of linear second-order systems, making control much more effective. To evaluate performance, the robot is commanded to follow the same reference trajectory using both PIT control and computed torque control. The results clearly show that PIT control, that is proportional integral derivative control, exhibits tracking errors due to unmodeled dynamics. In contrast, computed torque control achieves faster convergence and significantly reduced tracking errors across all joints. Now, I will run the simulation to demonstrate the closed loop behavior of the system. As here, the working tree is generated. Now running the model in Simulink. Here are the waypoints which I have defined here. The results can be shown in the scope. Now, to conclude, this project demonstrates a complete end-to-end workflow for robotic manipulator control, starting from mechanical design and moving through simulation, dynamic modeling, and non-linear control. The project highlights the effectiveness of computer torque control. Simulink and Simscape Multibody provide a powerful environment for developing and testing such model-based control systems. Thank you for watching.